Hello everyone. Today we'll be looking at altitudes. So let's start off with some vocab. An altitude of a triangle is a segment from the vertex to the line containing the opposite side, meeting at a right angle or perpendicular angle. So right or 90-degree angle. Every triangle is going to have 3 altitudes. They will meet at a point known as the Arthrocenter. Now folks, that being said, Arthrocenters aren't always going to be inside the triangle, but a little more about that later on. So let's take a look at some examples. Altitudes of the triangle. So given these triangles, for instance, triangle ADB, DC is an altitude, but the altitude exists outside of the triangle. In HEF, EG, the altitude exists inside the triangle with a 90-degree angle. Triangle LOM, MN is an altitude, but it exists outside the triangle. And in KIJ, we have an altitude at KI, forming the right angle, also making this a right triangle. So segments CD, EG, IK, and MN are all altitudes. On the other end of things, here we have an angular bisector going to some point on the line. This MO is not an altitude. We also have a segment bisector here. Could be a median of QS. QS is not an altitude. And then we have VY. We have our perpendicular angle there, sure, but it's connecting 2 sides. VY is not an altitude. To have an altitude, it must go from a vertex to the opposite side at a 90-degree angle. And it can be outside the triangle. So let's take a look at some specific triangle types. In an acute triangle, 3 sides, all sides are less than 90 degrees. The 3 altitudes will be inside the triangle. In an obtuse triangle, 1 angle is greater than 90 degrees. 2 of the altitudes will be outside the triangle, and 1 of the altitudes will be inside the triangle. Finally, in a right triangle, two of the altitudes are the legs of the triangle, which make up the right angle. This is going to be a very important way for us to determine if something is a right triangle or not, while 1 altitude will be actually inside the triangle. So for a right triangle, here's 1 altitude, here's another altitude, and there'll be a 3rd altitude in the triangle somewhere. All right. Now, the guided practice for this, folks, is actually going to be done in a separate video through GeoGebra, but I'll do a bit more explanation of that in a moment. So the Arthrocenters, folks, can exist in different places. For an acute triangle, the Arthrocenter will exist inside the triangle itself. Basically, the point of concurrency of all 3 altitudes will exist inside the Arthrocenter. In a right triangle, the Arthrocenter will occur at the right angle itself. But for an obtuse triangle, I know this is a little, perhaps not the best image. We have the Arthrocenter actually outside of the triangle. I'll show a little bit more about this in my other video. Now, these examples here would like us to find the vertices of ABC given our coordinate points, to find the coordinates of the Arthrocenter of ABC. And we could go through this. We have our points here. We could do that a few ways, one of which we could find where the altitudes of 2 of the lines of two of the sides intersect. We can do that using the perpendicular slope equations. And wherever those coordinates are, we'll have the orthocenter. In this case, we see the orthocenter is kind of marked out for us already at what looks like 7, 6. But there's another way to do this, using the GeoGebra program. And this is something I'll demo live in class along with the guided practice. After I demo it in class, I'll also make a GeoGebra video. However, that video will be silent as I cannot record audio on my desktop. So we're going to stop there for now. Please, folks, come back later on to watch the GeoGebra video for the rest of the guided practice.